You guys remember you're not coming to class Monday, right? I'm not coming. I'm going to sleep in. You know, till the internal body clock wakes you up at the same time and you go, ah! So then you get up, go to the bathroom. I get back in bed and roll over. I can go back to sleep. I can turn my brain off. My wife, no, she's up. So we'll see how Monday goes. Any questions you guys have first? I want to see if you, in studying this liquids or gases or even projectile motion that's rubbing you wrong. Okay. We started liquids last time with pressure being a force over an area. We're familiar and I hope comfortable, more comfortable. That's probably at least safe with forces. And now we start acting them over areas. You can do that with solid objects, but you can also apply that with liquids and gases. Lump those together, fluids. And they're usually microscopic. And so that's why we lump them together kind of macroscopically and use pressure comes in handy more than trying to add up all the individual molecules. And we had density, being the ratio of mass to volume. How much stuff do you have compared to the space you try to make it fill up? You can adjust those two and change something's density. And then I did a little derivation to convince you that it was the same formula, but rewriting it as the pressure in a fluid is dependent, proportional to these three things: the density, acceleration due to gravity, and the depth, how much of that fluid you have on top of you, which applies to, again, to liquids, scuba diving, maybe what you're more familiar with, but as well as air, the atmosphere. The more atmosphere you have above you, the greater your depth, the greater the pressure acting on you. We'll revisit this, well, either at the end of the lecture or next time. But think of all the weight of air. It's little, but if you have a lot of it above you, it does have some weight, and that's acting on you. So it exerts a pressure on you. This is another way to figure it out. Just how much of it above you do you have, the depth. And then at the very end, I introduced buoyant force. Put things in a fluid, water, and most of you know, I hope, before I put my foot in my mouth, but has anybody in here never been in a body of water? Just curious. Bathtub, swimming pool, hot tub, lake, so you have. All right. And you feel lighter. That's the buoyant force. We did something that was over here with a spring scale, and I put the cylinder in, and those of you who were here saw that its weight decreased. The scale reading decreased. We didn't change its mass, but the force that it took the scale to hold it up decreased. And that was because the water was helping support the object's weight. That was due to a buoyant force. So one way to think of that is your weight in air, in that case, minus the weight in the fluid. I don't want this to seem like an equation. I want it to seem more like, oh yeah, that makes sense. I weigh 170 pounds. In the pool, I guess I should figure it out. I don't know what I weigh. I could figure it out, but argument's sake, I weigh 150 pounds. So the buoyant force would be 170 in air, 150 in the water, 20 pounds. And I would know that's due to the water pushing back up on me, a buoyant force. Still a force. It's a, yeah, that's all I wanted to say. It's still a force. Archimedes' principle. That says that another way to look at the buoyant force is the weight of the displaced fluid. That's what Archimedes figured out. If an object is in a fluid, however much of that fluid it displaces, weigh it. And that's going to equal the buoyant force. We did that right at the end. We put that object in the water. We saw the buoyant force acting on it and the scale reading go down. But when I put it in at the same time, it displaced its same volume in water. I had it overrun into another beaker. When I poured that exact volume of water, which is the exact volume of the object, back into the system, it exactly balanced the weight that we saw decrease due to the buoyant force. The weight of the displaced fluid is the buoyant force. So there's like two ways you can figure it out. But that's what Archimedes rationaled. Okay, so I like this game. Weight of displaced fluid. We know how to figure out weight. That means mass of, first, I don't have to write that out every time, displaced fluid. And it's being accelerated down due to the acceleration due to gravity. That's how you find weight, right? Do you remember that? So there's so much mass of this fluid that gets displaced. And if we write the mass in terms of density, since I'm covering it up, density is mass over volume. So mass is density times volume. Get over here. I'm just going to replace the mass, put it in terms of density. It's the density of the fluid times the volume of that displaced fluid. That's the mass times gravity. I do these two formulas to emphasize up here. Pressure exerted in a fluid is not dependent upon the volume. I'm trying to emphasize it, it doesn't always stick. The pressure doesn't care how the volume of water above you, just how deep you are, just the height. The buoyant force doesn't care about the height, it cares about the volume of the displaced fluid. More particularly when you start doing problems and thinking about this, it doesn't care how heavy something is. It's weight. The buoyant force does not care about the object's weight. If I jump in a swimming pool, and my friend that's over 400 pounds jumps in a swimming pool, the weight does not determine the buoyant force. It's the volume. And the volume of the fluid displaced is directly proportional to our volume. How much of us is underwater? So let me ask you, if I'm in a hot tub, a swimming pool floating, treading water on the top, and the water level's about here, so I'm half underwater. How do you think the buoyant force on me compares to when I go underwater? Yeah, there is a difference. With only half of me submerged, will I displace as much water? There's less of me underneath, so I'll displace less water. If we weigh that, that's the buoyant force acting on me, and it'll be smaller. If I go completely underwater, now I have a greater volume underneath, I'll displace more water. The weight of that displaced water will be the buoyant force. My buoyant force just increased. So when something's floating on the top of a surface, it's not completely submerged. Only the part that's displacing water affects the buoyant force. But more importantly, more generically, the volume determines the buoyant force.
And the reason we're lighter when we're in the water is because the liquid is denser than the air. Is that right?
The reason we feel lighter is because, yes. Let me ask it this way, Kate. Is there a buoyant force acting on you right now? What do you think? What you got?
Yeah, I would say.
Due to what? She says yes.
Well, just due to that I'm sitting in a chair, there's some support force, but that's not.
The chair is a support force, true. Are you in a fluid?
No. Oh, wait, I'm in the air.
Yeah, we are in a fluid, air. We're just so used to it, we don't notice it, and it's really, really less dense. The density of air matters. The density of the fluid. So in air, we are taking up a certain amount of space in this room. We're displacing a certain volume of air. If we could weigh that air, the weight of that displaced fluid, that would determine the buoyant force acting on us right now. So yes, there's a buoyant force acting on all of us right now because you're displacing air. Is it much? Heck no. But we do. So when you jump in water, what changes? Gravity? No. Our volume? No. But the density of water is a lot bigger. So is the buoyant force we feel, and now it becomes apparent to us. So I know you got questions. I thought of something. So if I stand on a bathroom scale and read 170 pounds, if you could get rid of the air like that and still stay alive, what would the scale reading do? It would be higher. Not much, because the buoyant force due to air is but yeah, it should increase. If you had a sensitive enough scale to tell, yeah. Okay, now we had some questions.
Just have a question. It might be totally off, but is that why it's harder for a heavy person to go upstairs than it is for a small person?
Is that why it's harder for a heavier person to go up the stairs? In general, a heavier person has more volume. That's the key, not the weight. Just being heavier doesn't, more volume. That would actually mean the buoyant force on a large person would be greater. So they should actually feel a little lighter. So if it did anything, it should make it easier for them, but it doesn't. No, that's just health. Why it's hard to go up the stairs. Got it? So I know I say it here simply. I hope you're making notes, or at least mental, so that you can refer back to this when you're rereading the chapter and doing the questions. To be redundant on purpose, the pressure doesn't care the volume of the water above you, just how deep you are. So you can be in a skinny container or the ocean. If you're 10 feet under, same pressure, as long as it's both water. The buoyant force doesn't care how heavy the object is. It's the volume of the displaced fluid. How much of that fluid is getting displaced, which is dependent upon the volume of the object that's under the fluid. Now, what makes you sink or float? Let's move over here. This part, I hope, should make more sense to you. You want something, James?
I think I understand it. Isn't it sort of like how a ship works?
How a ship works? What do you want to tell me?
Doesn't it displace more water than it weighs or something?
It says a ship displaces more water than it weighs. We can answer this now. A big ship, is it heavy? Yes. Yes. Does it have a big volume? Yes. So it has a lot of mass, but it has a lot of volume. What's that do to its density? Yeah, if you can spread that mass over a big volume, you can keep your density fairly low. And we know that, well, Let me do this for you. I think it'll make more sense after this. I hope. So, we have a weight down, some object. Force, weight. If it's in a fluid, there's a buoyant force. Somebody's stealing my table. And now we just have to figure out the net force. Is this object going to change its motion? Is it going to move up, down, or stay put? Well, it's the same game. If the buoyant force is greater than the weight, it'll start rising up. A helium balloon, a bubble underwater. If your buoyant force is not as great as your weight, you sink and you go to the bottom. And if they're equal, you're floating right wherever you're at. Usually in normal terms we say something's floating this works. It's not moving up or down now, so it's raised out of the water, but I know now that its buoyant force exactly equals its weight because it's not going up nor down. How much water is it displacing? Not its whole volume's worth, just enough. It's displacing enough water that weighs the same as the boat. You see that? It's displacing just enough water, and that amount of water weighs the same as the boat. The way to displace fluids, the buoyant force, and the buoyant force is balancing the weight. That's why it's staying put. That's how you know something sinks or floats. So, if you have something that, we know cement sinks. Ka-chunk. How does the buoyant force compare to the cement's weight? It's less, because it went to the bottom, and now there's a support force from this holding it up. But the buoyant force is not sufficient. The buoyant force doesn't care how heavy it is. That relationship determines whether it sinks or floats. The buoyant force is based on its volume, how much water it displaces. Is it displacing enough weight of water? No, but the boat is. So another way to look at this one's cement as well. It's the same, roughly. Volume. So even if I push it underneath, so it's completely submerged right now, what's the buoyant force on it compared to the one at the bottom? If I hold it under the water, how do the buoyant forces compare? They're the same. It's based on volume. They're both, if they're the same volume, they're displacing the same volume of water, same buoyant force. Well, what determines whether it sinks or floats? It's weight. So you can get a gauge here about their weights. Which one's heavier? The one on the bottom. The one on the bottom, the weight is more than the buoyant force. The one on top, the weight is less than the buoyant force. Weight at this point. Now, does that make sense? Do you see that the buoyant force is the same if they're both submerged? Because they're the same volume. Okay, good. So I've let go of it. Now which one has the greater buoyant force? The one on the bottom. Good. Because it's displacing a larger volume. It's completely underwater. Where the one floating, you see how some of it's out of the water? It's not displacing the same volume of water as the one at the bottom. So its buoyant force is a little less, actually, than the big one. And this is where I don't want you to get confused. See, the big one is feeling a greater buoyant force, but it's sunk. This one feels a lighter buoyant force, but it's floating. Because what's the buoyant force trying to counter? It's weight. If the buoyant force, this is less buoyant force, but it's still more than this guy's weight. So he floats, because this guy's really light. You can come up and feel these afterwards if you want. This guy has a big buoyant force, but he's too heavy. Yes? Yes.
So why is it lighter?
Great, now we can get to, yeah. And that is, this one's a whole lot more dense. In order for this one to be heavier, but take up the same volume, it must pack more matter in the same volume, in the same space. So same volume, but a lot more mass. So that's why it's heavier. This one's more dense.
They're both concrete.
They're both concrete. This one has more air mixed in with it. It's a concrete air mixture, but yeah. There could be different types of concrete too. I don't know. I didn't make them. I found them. But
So one of those was made out of styrofoam, but it was the exact same volume, and they were going to submerge and one was held down. They would still have the same boiling rates.
yes. If one of these was styrofoam, same volume though, both submerged, if they're displacing the same volume of water then they must have the same buoyant force. Because buoyant force is dependent on volume, not weight. Whether it sinks or floats determines whether it's a big enough buoyant force. I just find that curious though, because remember again, this one's sunk, completely submerged. Greater buoyant force, but not enough. This one floats out of the water a little, less of a buoyant force because it's not displacing as much volume, yet it's enough to overcome its weight and make it float. So density, this one's more dense. Another way you can look at this is things that are less dense than the fluid they're in float. Things that are more dense than the fluid they're in sink. This is more dense than water, it sinks. This is less dense than water, it floats. It's kind of a shortcut, but now you know why. You reason all that through. Why we're over here floating, I like this one. I call it root beer float. I have diet and regular. Regular sinks, diet floats. You know why now, tell me. What can you deduce from this? What do you at least know a little bit of? This one must be less dense than water. It's floating, correct. Okay, why do we think it's probably less dense? Because it's diet, of course. No, it's the sugar content. This has a whole lot more sugar than this one. They replaced the sugar with, what's this one? Aspartame? Yes. So it doesn't take near as much aspartame. But the point is this is less dense. Same volume, but while I'm over here, I'll do some more. You saw that floats? Because I always like to do origami. This one floats. They're about the same mass, you have to believe me. So, if I make this more dense, how can I make this more dense? Yeah, I could put stuff in it, right. You load it up. And that could be the equivalent of, it's getting heavier and heavier and heavier. I heard somebody else say something to you, I can crumple it up. So you tell me, did I increase or decrease the density? Did I change the mass? No. Now will it sink or float? Nope. It still must be less dense than water as a unit. The buoyant force is balancing its weight. It's displacing just enough liquid, water, to balance. So let's make it more dense, right? Get some of that air out of there, right? All right, what do you think now? There we go. Now, it must be more dense than water. And it's the same mass. I've just concentrated the volume, eventually got small enough that its density got larger than water and it sank. It's now not displacing enough water because it's a smaller volume. It's not displacing enough water to create a buoyant force enough, sufficient to balance its own weight. And if you ever want to feel buoyant force, try to put a balloon underwater. Oh, geez. Because it displaces a lot of fluid. That's a big volume. That volume of water weighs more. That's why balloons float so darn high. There's like hardly anything under the water. It's displacing very little water, which weighs very little, so the buoyant force is very little, but that's all it takes to counter its weight to make it float. So next time you're taking a bath in the hot tub, whatever, you can praise or curse Archimedes, I guess. I better talk a little more before, while my hands dry before I touch my laptop. I'll do these two then. These are balanced, you see? They weigh the same on both sides. I'm going to push my finger into the water. I'm not going to touch the bottom. I'm only going to touch the water. I'm not going to touch the sides of the container or anything. What will happen when I put my finger in the water? You still think this side will go down? My finger will just push the water to the side. Get it out of the way so my finger will fit in the water. Does anybody think it'll stay balanced? I did. Here you go. I'm not touching the bottom. That one I bumped it. But you get the idea. Yeah, my finger is just pushing the water to the side. But what happens to the water level? When it's doing that because I'm displacing that fluid. How much? Well, whatever volume that is. You weigh that? Well, there must be a buoyant force acting on my finger. And which direction is the buoyant force? Supposed to say dry. The buoyant force is up. I'll get to that in a moment.
Is that like Newton's third law?
And then it's exactly, that's what I wanted to say before I draw the up picture. Newton's third law. Buoyant force is up on my finger. The water is helping support the weight of my finger. It feels a little lighter. I can't tell, but technically. So if it's pushing up, there must be a reaction force down. If the water is pushing on my finger, then the finger is pushing on the water. And that translates onto the scale, and the scale gets pushed down by not the weight of my finger, but by the buoyant force, the weight of the fluid I'm displacing. That's how much I increase the weight on this side, force. Now, why is it up? Your book draws some great pictures on this, probably better than I do here, but if something's in water, is the pressure larger here or here? At the bottom. So if I represent that with some arrows, it's kind of like that. There's pressure up here and there's pressure down here, but the pressure is larger at the bottom than it is at the top because there's pressure on the sides. Can't get rid of those, but they cancel each other. So the net effect is the buoyant force acts up. Do you see that? And that's just because it's a little greater the deeper down you get in any fluid. I love this stuff. It's kind of fun once you wrap your head around it. Okay. Here's a fun one then. This is water, so is this, but I've closed it off. There's a little air inside. Do you think it'll sink or float? It floats. So it must be less dense than water. And right now the buoyant force equals its weight. It's displacing enough volume. Almost all of it's underwater, but not quite all of it. This is what I really want to get to. I'm going to pour some cooking oil on the top, and this will take me forever to clean up, but you're worth it. This is cooking oil. What will happen? I'm going to pour it in on top. What will the oil do in respect to the water? It floats. And you know this because it is less dense than water. Very good. Well, now instead of this top part being in air, this little top part feels a buoyant force due to the air it's displacing. That's helping hold it up as well. We're going to replace the air with oil, which is a lot more dense. How do you think the buoyant force will affect that top part? Do it this way, maybe we won't get as many bubbles. That's why I colored the water to help you visualize. The water oil line is right here. You can see the oils floating on the water. And yeah, the blue object raised up. Only this much of it needs to be underwater, and this much is sinking. It sinks in oil. It floats in water. Both are contributing to a buoyant force, though, dependent upon the density of the fluids.
Why do oily liquids come to the top with another liquid, like vinegar and oil? Or
Because
why does the oil always come to the top?
they're less dense. Yeah, they still have weight. And so they must be displacing, in this case, this oil must be displacing a little bit of water. So if the water level was here and I pour oil in, the oil must cause this water to displace a little. It's usually insignificant, but that creates enough buoyant force to hold up the depth of oil. Same thing, they'll just treat the oil as an object now. It's putting in, it must be displacing the water, which creates a buoyant force. It's like the balloon. It doesn't take much because it's less dense. So less dense. You know what I mean. But it all has to come into play. Did that help?
Well, it just seems like if you put two liquids and one's denser than the other, the denser one would go to the bottom.
Yes. Two liquids. The dense liquid will sink to the bottom, and the less dense will float to the top, just like oil and water.
Okay, but like,
You're right.
if I put like chicken broth
Mm.
in the refrigerator, now maybe it's because it gets cold, but it's the way you can skim off the fat, because the fat.
Chicken broth in the refrigerator. When it gets cold, yeah, density, temperature can affect density. And so the fat that settles on the top is less dense than the broth. And less dense things will float. So the fat comes up to the top and then freezes and congeals. Yeah, and you can skim it off or peel it off. Oil is less dense than water. Fat is generally even, well, broth, it has a lot of water in it. The fat is like the oil. It's less dense and it's going to start floating on your broth mixture.
So an oil is less dense than water.
Yes. Did I say that wrong once unintentionally?
More dense than air.
Say that in what?
Oil is more dense than air.
Oil is more dense than air, yes.
When you were saying that, that's where she was getting confused.
Yeah, the order is air is less dense, then oil, then water.
It just seems, because it's thicker, it seems denser.
Ah, maybe the viscosity, another term. Viscosity is like how well it flows. Water is less viscous than maple syrup. It doesn't flow over, but that is different than density. So yeah, oil is generally more viscous than water. It doesn't seem to flow as fast, but that is unrelated to density. Maybe that's what was getting you.
Well, I took the Diet Coke thing. I thought with sugar, that makes it thicker syrup.
Yeah, that you have to look at the can and the whole thing, because you got all kinds of things in there, including air inside the can. But as a unit, the Diet can is less dense than the full. On that vein, let's do this one. These are ketchup packets I got from Carl's Jr. Filled it in, they're in water. They must be more dense or less dense than water? Less dense. So they are displacing more volume of water. That water that they displace weighs more than its weight. That's because they're trying to come up, but I have it sealed off. You follow that? Well, can I change things? I'm going to squeeze the bottle, which increases the what inside? The pressure, the density. Yeah, I'm going to try to contract that mass into a smaller space. Yeah. And look what happens. You can amaze your younger brothers or kids or nephews and nieces. Okay, concentrate really hard. I want you to think, make it sink. Come on. You're not doing it seriously. You know, you can ham it all up and you're doing it, you're doing it. And they think you're magic. What's happening? There's ketchup in the packet. There's also an air bubble. And what gives, I push the bottle pushes the water pushes the packet pushes the ketchup, and the ketchup pushes on the air bubble inside. And the air bubble gets smaller because it's feeling the pressure. And if the volume gets smaller, what happens to the density of the ketchup packet? It increases. Smaller volume, bigger density. And if I squeeze enough, I can make the ketchup packet's overall density larger than water, greater than, and it sinks. When I release the pressure, that air bubble can re-expand, decreasing its density, and it can come back up. Notice the other one's not going. I must not be decreasing its volume of air bubble enough. Let's see. There we go. That bubble must be larger. Well, that was harder. All right, you get the idea. Think it'll sink or float? It's full of lead shot. Oh, it sinks. Wait, it floats. Ah, it floats. It barely floats. I mean, it's barely just submerged. So it's almost completely under. That tells me the density of the sphere must be almost the same as water. Slightly less. This is water. It floats. It sinks. It sinks. Oh, yeah, it sinks. They're both water. And only water. Magic. No, the pictures don't matter. There's not something hiding under the table here with a magnet either. What? That's not how I dropped them in. Temperature. Well, yeah, I'm not going to have you relate, but no formula for this. But warm water has a slightly different density than cold water. Because you know how when things get hot, they expand. When they get cold, they contract. Well, this thing is so balanced just right that, yeah, it floats in cold water, sinks in hot water. It's pretty warm. Warm water, if it's less dense, less dense things can't provide the same buoyant force for the same volume. It's a little bit less, not enough to support its weight, and so it sinks. But cold water is slightly greater density, and it's sufficient now to support its weight. So that's the difference between salt water too and normal water. Salt water is more dense. So salt water can create a slightly larger buoyant force for the same object. And so that's why it's easier to float in the salt lake. And I did it again, got my hand wet. Let's ask you a few questions. Clickers. See if you guys can put some of this reasoning together before we cover a new concept. Yeah. Once the projector warms up. Replace lamp. All right, we got another one, Catherine. Gotta have this thing up first. Okay, now polling's open. Whew. Where'd it go? Sheesh. Okay, go! Hallelujah. When you stand on one foot instead of two, the force you exert on the floor is? Not giving you as much time. Put it in there. See what you think. Oh yeah, you guys are going fast. Look at you go. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 84% for B. And the correct answer is the same. You're the same weight, same mass. You didn't change that. What are you changing? Very good. That's the next question. Don't have to ask you now. I want this one. Go. Water pressure provided by a water tower is greater if the tower is what? You know, they put water towers up there so that they can create a pressure so that we get it in our you know, when you open your faucet to wash your hands, you got pressure. You can affect that pressure by one of these things or both. Make it taller, make it hold more, or both. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 65% for C. Now, how come sometimes it shows you guys the results and other times it doesn't? I haven't figured that out yet. So most of you thought both. Correct answer is taller. Pressure is dependent upon depth, height. It doesn't care how much, just how high up you are. So you can make that water tower a mile wide and hold a whole lot more water, but if it's the same height, you're going to get the same pressure at the bottom. It just matters that column above you. So don't be swayed by it. Whoa, that's a lot more water. Yeah, in total, it's going to be a greater weight. Yes, it's going to weigh more. But pressure is related to force over area. And so over your given spigot, it's going to be the same pressure for the same height, same depth. Does that make sense?
Yeah, so why do they build them, the big things?
So they can hold more. So if they need to actually use the water or drinking water, you have more. But the height alone determines the pressure. It's good to have a bigger reservoir just to have more water. But there's some others in here I liked. No, I don't like that one. Let's do this one. Go. How many forces act on a submerged body at rest in a fluid? It's underwater and at rest. Or it's in air and at rest. But you can make your life easier. It's in water, it's submerged, and it's at rest. Oh, I keep forgetting to ask. Somebody in here asked me for some book references about Newton. Is he here? Because he hasn't sent me an email yet. I have them all ready. Guess not. Okay. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and overwhelming B, 80%. 2 is absolutely right. If it's at rest, its velocity isn't changing. So there's no acceleration, there's no net force. That means at least two forces must be balanced. And in this case, yeah, it's its weight and the buoyant force. It's not sinking, it's not floating. All right? Which submerged block has the greatest buoyant force? Think about what's buoyant force dependent upon, and based on these objects, it's given you their masses. What can you deduce? Your clue. Buoyant force is dependent upon mass or volume. So you need to figure out, do these have the same volume or not? A little trickier, huh? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and oh, it's pretty split. 30% A, 40% B, 28% D, no takers on uranium. But most of you thought B. The answer is B. They're all the same mass. Which one is less dense? Aluminum has the lowest density. We're taking that for granted that most of you would realize that with uranium and lead as your other options. If aluminum is less dense, to fit the same amount of matter, same mass, it's got to take up more space, doesn't it? So it's going to have the largest volume and thus displace the most water and have the greatest buoyant force. Buoyant force depends on the water displaced, which is dependent upon the volume. And aluminum is going to have the most volume if they're all going to have the same mass. Yes?
Would you have a question like that on the test without indicating which one is more or less dense?
I think to be fair, I should tell you which rate the densities. I was taking for granted that, well actually I didn't write this one, but nope. 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 We'll make this the last one. Free you. Go. When a submarine takes water into its ballast tanks, its density does what? This is how fish in submarines float or sink. How do they move down there? They got to change something. Fish have an air bladder that they expand or decrease. And submarines take water on or get rid of water. So when a submarine takes water in, what happens to its density? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 92% B. Good job. You're getting it. So it changes its density and changes its buoyant force so that it can sink or float, whether it wants to go up or down. Very good. All right, have a great weekend.